Okay, so we have our x, y, and our z. And for every value of z, for every value of x and y, get a value of z. Okay, so for our given values are x equals 2 and x and y equals 4. Well, for the given equation, z equals x squared plus y. So plugging in our values, we get 4 plus 4 is 8. So if we plug this on to our coordinates here, this is our y and this is our x, so we would go 2 over, and then we would go 4 this way, and then we would go 8 up. Going straight up, 1, 2, 3, 4, 5, 6, 7, 8. And we get our point there. So that is how you graph in 3 dimensions. Okay. So we would like to graph x squared plus y. Okay. We would get this 3-dimensional object here. Okay. So we C is equal to x squared plus y. So when we get a partial derivative, we are taking the derivative of z with respect to x. So what would that look like? So when we take the partial derivative of z in terms of x, we take the partial derivative of z in terms of x for the equation that we had above, which is x squared plus y. This would mean that we are holding y as a constant. So we would get 2x. If we do the same for y, in terms of with respect to y, we get 1. So let's choose a y value to hold constant, just so we can visualize this. So we're going to take the y value of 0.5. Okay. Kind of difficult to see with this color scheme here, but right here we have this. When we place this plane, so you can see this plane here, when we place this plane inside of this graph that we've already have of x squared plus y, we get this line, or a curve. We get this curve created, and on this curve there's tangent lines at each of these points. Simply the same kind of curve as a parabola, for instance. So when we take the derivative of, say, this would be x equals 0.2 at that point right there. So at that point right there, there would be a tangent. And when you take the derivative, partial derivative, of z in terms or respect to x, you get a number, which is this tangent. So that is specifying it, because otherwise you would have an infinite amount of tangents at each of these points. So at this point right here, you could have an infinite amount of tangents without any specificity to whatever direction it is in. Okay, so let's just try out a new problem here. And so our equation is going to be, this is x. Z equals x squared plus xy plus y squared. So the partial derivative of z in terms of x would be, I have to change this because I was doing it in terms of y before. So a partial derivative in terms of x would be 2x plus y. So let's write that in there, 2x plus y. Okay, so we have 2x plus y as our derivative here. So let's take the x and y value of 0.3 and 0.1. Okay, so in terms of x, which means that we're going to be taking y as a constant, so 0.1. So we're going to throw this in here, as I've already graphed this, is x squared plus xy plus y squared, and we have y as 0.1. So this is graphed as a wall because we're keeping it constant. So, for instance, just to clarify this, when we plug this value of 0.3 back into our equation, our derivative here, this would signify that the partial derivative of x, that's a d, is equal to 2 times 0.3 plus 0.1. Okay, so you're going to get a value. This value would be, so for at 0.3, so at 0.3, the derivative, partial derivative of z would be a value at that 0.1. So that is the introduction to what this, what partial derivatives mean in the visualized form.